Crossmath is a popular puzzle game where you have to solve math problems. But what if a bot could play and even beat human players? That's exactly what I've created. In this video I will explain what the game is about and then explain the algorithm and theory used to find a solution for the game, including optimizing the search algorithm and my thoughts on the state representation. Then there will be a bit about how I use classical image processing to extract the information from the image. This was actually the first part that I solved. And then I will show how the pieces come together using Python and Android Debug Bridge. And finally, I'll be thinking a little bit about, and definitely also asking for your comment, how we could create an abstract bot tool. Some facts about the game is on the screen. So it's made by Guru Game. You can see the link here. So the objective of the game is to solve the equations by moving the numbers from below up to the top. And to begin with, the equations are super simple, just having one variable per equation. So there is really only one correct combination up front. Whereas when the difficulty increases, there are several solutions to the individual equations, thus increasing the amount of elements we need to consider. Here I'm drawing with purple when there is only one variable, and with cyan when there are two, and in red when there are three or more. So in Crossmath, the main part driving the difficulty is the number of combinations that needs to be considered for each equation. I'm saying the main part. For the bot, that is the only difficulty. For a human as me, different operators and big numbers are also more difficult. So, you know, the number 75 is more difficult than 1 and 10 for me. Yeah, I'm drawing the purple when there's only one variable, cyan when there are two variables, and red when there are three or more. But in Crossmath, the main part driving difficulty is the number of combinations that needs to be considered for each equation. I'm saying the main part driving difficulty, for the bot, that is the only thing driving difficulty. For me as a human, the big numbers are also driving difficulty. For the bot, not so much. One way to create a bot that solves the game is to try all combinations, basically to loop over all the variables and fields and try a combination. So let's try to have a look at how the computer experiences that difficulty. So to begin with, we have a look at an easy sample. So one variable, one field, and there's not really anything to think about. So here we have two variables and two fields. Shouldn't be a lot to think about, but we know we can make one wrong combination. And then we have three variables and three fields. And well, there are more than three combinations. I'm just showing the edges here. So let's show this difficulty using graph theory. So first I will convert it into a bit different format so I can annotate how the computer would think of these states. So for the game state, I have named all the input fields, input areas, the area above, A1, A2, A5, and the variables I can insert as alpha. So for the first one, there is nothing to think about. What we need to do is to move alpha 1 to A1, and then we have a solution. So we are doing the same here on the next. The x's are different, therefore the numbers will be a little bit different. If you get the principle. Here we are starting by moving alpha 1 to A1, and then we need to move alpha 2 to C1. The equations, this was not the correct solution because it's 1 minus 6, that's not 5. Then we need to backtrack. and we are trying a different variation here now, and we find the right solution. So here the computer needed to make 5 different of 4 moves. Four moves, yeah. So let's go to the difficult here. I don't remember if I mentioned it already, but in graph theory, the circles here are called nodes, and the line between them are edges. And the node represents where the numbers are in the top and the bottom, and the edges represent what we did to get to that state. If you don't know about graph theory, I can promise you it's an interesting topic, and invite you to search a bit on it. You will not imagine how long time it took me to draw this. You can see there are really a lot of moving around for a computer, inserting the number that you actually need to do. And here we find the solution. After 13 moves, after visiting 13 different nodes, we actually find the solution. You can see the solution is alpha 1 to A5, alpha 2 to A1, alpha 3 to A3. And there is a few more solutions. There are a few more variations we could actually do, and it turns out those variations would also be a solution, but the point is, to begin with, we just have 1 move we can do, then we have 4, and for the 3 variables here we have 15 moves we need to do. So first I changed the representation. So instead of having the variables alone, I create all the equations with a reference to the variables. Then in each move I evaluate the equation that was impacted and only continue searching that path in the graph if the impacted equations are true or still have open variables. Let me show what I mean. So here I've made a super simple cross, so you can see we have 1 variable here, we have variables here. So if we write these equations separately, and now it becomes obvious which one is easiest to solve. Let's, by the way, call them a name. Now with these names, well, let's see how the algorithm would work then. I would start by taking this equation because it only have 1 variable, and then I would solve it. Okay, I might try 2 combinations, but in the end I would figure out it's 3. So we would get a 3 here and here, because that's the same variable. We would continue down that path, and now there would only be 1 left, so we would easily get the solution there. I hope it makes sense. Yeah, as mentioned, when selecting the equation to solve first, I select the one with the fewest number of variables, just as I did as a human when I was playing normally. But you can see from the table here below the impact of the sorting, and it's pretty hefty, I would say. So you can see the first column is I call it the worst, but it's actually to make the algorithm as dumb as it could be. So here the algorithm is selecting the equation with the largest amount of variables first, and I don't know how many are there. 1.4 million nodes on the difficult, which is completely terrible, of course. And the no sorting is then where the equations are not sorted. So basically we just take them from top to bottom, left to right. And then finally there is the optimized, which I spoke about, which takes the equation with the fewest number of variables first and then solve recursively. So before we get to any of the actual solving the puzzle, we need to feed the algorithm, which means we need to detect the puzzle game. And I do that using classical image processing. Let's have a look at how I do that. So the first part is the segmentation, where I find the areas, then I do classification, and I do detection, which is basically reading the symbols. And then I save the data. So let's have a look at the details. So here again we have the flow, so I detect the top and bottom, so you can see down here I detect the top and bottom, and then I refine by removing text and circles. I find the top grid, I find the bottom grid, and I classify the top grid. I'll get to that. And I read the symbol and the operators. In the bottom I don't need to classify anything. Anyway, let's see what I mean. So here I detect the top and bottom grid, and I do that by doing an edge detection. If you're interested, you can go to my GitHub and you can look at here. I think we can open the file and see. But I will not go through this. If anyone is interested, I can do a walkthrough of the content here. But for now, trust me when I'm saying I'm using classical image processing. I will find, first I find these areas. If you look at the game here, you can see there's a black line and there is the gray up here. So I find this edge and I find the second edge. And the same down here, I find the edges. I find the edges on the side. And from that I can select this field and I can select the other field here. In the upper field I still have this text, so I do one more edge detection. So I do a binary image here. I remove this thingy up here, and then I get to just the fields I'm interested in. For the bottom it's the same. Just from the bottom I want to remove these circles and this stuff down here, and then again I have the stuff I'm interested in. So after that I need to find the grid, and for the top grid I find the grid by creating a binary image, and in the binary image I have the start and the stop. By doing a projection here you can see where my mouse is, so that's the end of the grid and the starting of the grid. And the same, this is the start of the grid row, and down here we have the end of the grid rows. I then find the grid size by doing a distance transform and taking the maximum. So that will be the half width of the grid. And you can see here the red and the green is the overlay of that grid. So I hope you can see that it matches perfectly. Then I do a classification. And what do I mean by classification? With classification I mean I have the game field, but the game field can have three classes. It can be, you know, just background. If you imagine this entire stuff is a grid, you know, this yellow under my mouse here is just background, it's not interesting. And then under my mouse here we have a variable, an input field, and then the next field we have a symbol. I'm doing two distance transform, and by combining the values of those two distance transforms I know whether I'm in a background or whether I'm in a symbol or whether I'm in an empty field. And you can see down here I save the classification of that logic. So these are background, these bluish guys are empty fields, and the yellow guys are operators or symbols, whatever. Then the next thing I need to actually read the text, and I do that using cross correlation. So I have taken all the symbols, which is 1 to 9, and plus, minus, divide, and multiply. Then I do cross correlation of the symbols. Okay, I'm skipping one thing. So for instance, you see the string 14, that's actually 2 symbols. So I do a detection of whether there is 1 or more symbols by doing a horizontal projection of this binary image. And it might be difficult to see here, but between 1 and 4 there is no black. And if there's I know that if there is a black region separated by a non-black and then a new black, I know there is more than 1 symbol, and I can count that. And what I then do is I look in each region, and you can see the cross correlation, which basically means how well does it match with the original images. So you can see for the 1, you can see the cross correlation for the symbol 1 is highest, so that's obviously a 1. And you can see for this symbol, you can see the cross correlation. First it's highest for 1, and then after that it's highest for 4. So I know this piece of text is 1 and 4, so it's 14. Okay, and then in the bottom I actually find the rectangles a little bit differently. I just use a distance transform, and I take the center of the distance transforms, and that will be the grid. I don't remember why I used a different strategy, but this is actually simpler. I think for some reason it didn't work on the upper one. And then finally I save everything. So here you have the field types. That's this whether it's a background. So you can imagine we have the grid, 11 rows, 6 columns, and we have a background, we have a input field, and we have a symbol. So later when I need to solve the game, I actually don't remember what I'm using this for, but I guess we'll get to it. I need to know where the variables are, of course. And then I reconstruct the equations. So here we have the equations without any, here we have the symbols, so it's not equation yet. And down here we have the variables, and they are saved with a position because I need to be able to translate the solution to mouse clicks or to finger clicks, because it's on a phone. So I need to be able to translate it to finger clicks. But how I have encoded the symbol name, I didn't use alpha 1, alpha 2 as in the example, or A1 and A2. Instead I've used the row, column format. So here we say row 1, column 3 is a plus. So that means that this guy is a plus. And the same for the variables. So when I reconstruct the equations, I loop over this 2D array, and I reconstruct the equation by selecting the fields that are neighbors, and then I encode that. So this one would be one equation with 2 variables, and the variable name would be the coordinate in this field. Because that means when I then reconstruct, you see this equation, I cannot mark columns, but in this equation here, this field, well, it's a symbol. Let's see if we can find an input that has 2 equations. Here is a input that are a member of 2 equations. So now I know that if I encode this as row, column in the individual equation, and then when I try to replace that with a value, I will update both equations. So that's that's how I did it. If there are other ideas of how to do it, I'm very interested. So what I just showed, I'm calling contextualizing. So basically I'm taking those symbols and operators that are pretty much without context, and I convert that into a representation that's easier to interpret, loading the data as I was showing first, then putting it into, you know, the equations by looking at the neighborhood and giving them names that are easy for me to operate with, which was this row and column, and then finally to solve. Then I'm using Python and Android Debug Bridge to automate the game. Let me show. So the main part of this automation is that I have a while loop that just, you know, keep playing, and there is this step here which is the acquiring an image and solving the puzzle, and then there is some stuff here to skip advertisement. I didn't show that part because I bought the game, so this is actually not used. Let's see the grab and solve. I name the screenshot, so I have all the screenshots saved. I acquire an image from the phone. I invoke the image processing command, which is written in Octave and wrapped in a Docker image. I save the result to a file. I then call the solver, which starts by contextualizing, so it takes the same file here, do the contextualization and write the output to this file, which I then process here, basically just performing all the clicks. And then I do 2 clicks for going to the next level. Now, I have been talking a lot about the overview of this bot I have created, not really gone into any details, but one thing that I find quite interesting is how we could create a generic bot framework for solving games. So the different pieces I'm thinking of would be, you know, acquire, segmentation, and classification, then some kind of contextualization. We need to be able to react and solve. Maybe there could also be added some kind of machine learning. We need some way of interacting, and for different game we might need multi-states, changing goals, testing, especially for puzzle games. It's quite feasible to make testing. I don't know about, you know, platformer stuff like that, how to make testing there. It's an interesting topic. And then how to add a generic input, or actually both generic input and output. So we could use browsers, mobile and desktop. Okay, so let's just look at some random online games here. So what kind of generic stuff? What kind of generic stuff is needed to, you know, solve them? Some of them are quite complex, that's for sure. Definitely something like this space waves seem like it would be fairly easy to do. Changing colors is an interesting challenge. Billiard stuff, probably also fairly easy. A meme battle, that's interesting. Maybe an LLM. Yeah, anyway, I had a lot of fun while making this bot. So I hope you had some fun also watching this. And yeah, if there is something you want to know more about, you can write in the comment. And yeah, thank you for watching.